Okay, so now we're going to talk about continuity and differentiability. Now, continuity is something that you have touched on in your other classes, but maybe haven't seen a formal definition of. So we just talked about limits yesterday, and limits, um, in your Delta Math, there were examples where you talked about from the left, from the right. To be continuous, the definition means that the limit from the left is equal to the limit from the right, which is also equal to the value when you plug in the exact number. So however you want to write that in your own words so that you understand it, that's great. So when I'm talking about an example, maybe I have a graph that looks like this. Maybe I'm approaching my value of A here. And what I need to happen is that the limit from the left and the limit from the right approach this same value. And then it has to be filled in or continuous. It has to be a straight line. There can't be an open circle there in order for it to be continuous. So a counter example, I can draw a couple different ones, but I'll do two. So this one up here would not be continuous because it approaches two different values. And then this one would not be continuous because there is a hole in the middle of this. And we'll talk more about discontinuities as well. But basically, if you can't trace the entire function without picking up your pencil, then it is not continuous. So if I can trace the whole thing without lifting my pencil off the paper, then it is continuous. But here, if I try to trace it, oh, I had to pick up my pencil. Or this one, oh, I got to skip over the circle. I picked up my pencil. So that means it is discontinuous, okay? So the intermediate value theorem states that if f is continuous on a closed interval from a to b. So if a function is continuous, meaning I don't pick up my pencil from a to b, then c is any number between f of a and f of b, then there is at least one number x in the closed interval such that f of x equals c. Now, this sounds really complicated, but I consider it common sense. So if, let's say, this up here is a dot, let's call this f of a. And there's a dot down here, let's call this f of b. It's saying that somewhere in the middle, there is some x value. So the definition says that c is somewhere between these two y values and that x is somewhere between these two values. So basically what that means is that in order to get from this line to this line, it could be a straight arrow, right? There could be a straight line and there could be a value c where f of x equals c. It also could be a curve. Maybe my function looks like this. But it still crosses through a value of c. It could be this direction. And it'll still hit that y value at some point. It could be a total squiggle. And it'll still hit a c value. So I'll do that one more time, but I'm going to put a c value here. So here is c. So somewhere along this line, this y value is c, okay? Now, basically what this is saying is that in order to get from point A to point B and to be a continuous function, I have to pass through the yellow line. Oops. So I have to pass through no matter how I try to get here. Even if I try to wait till the very last second, I still pass through the yellow line. So there is no function where I can get from A to B without passing through that yellow line. So that's what the intermediate value theorem is. So the definition of differentiability is very similar to the definition of continuity. The only difference is this time you're taking the limit of your derivative. So moving from the right side, the slope has to be the same as from the left side, which has to be the same as the slope at that moment. So basically the slopes are the same from both sides. So an example of something that is differentiable at any given moment is a quadratic. It's a lot easier to think of examples that are differentiable, meaning you can take the derivative at any given moment. But there are examples where it is not. For example, think of an absolute value function. So in an absolute value function, the slope here is 0. The slope here approaching this way is closer to like -1. And the slope here is +1, which means this function is not differentiable at this value. So something we can think of, a little cheat sort of, is if it is differentiable, then it is continuous. But if it is continuous, it could or not be differentiable. And we can see that in this example right here. So when I'm looking at the absolute value function, it's not differentiable, but I can draw this function without picking up my pencil, meaning it is continuous. It's just not differentiable. So that is your lesson in continuity and differentiability. Those are all of the notes that I handed you in class, but I will give you this worksheet tomorrow on tangents. I thought I would just show it to you. Oh, no, never mind. I'm not. I'll wait till another day. That's 2 lessons. I'll go ahead and just let you focus on those 2 lessons. I'll post the Delta Math as well, so that if you want to take a look at it, you can beforehand. But otherwise, I will see you in class on Thursday, and we will work then.